Welcome to ePadasala lecture series in computer science. Last module we discussed about how to write algorithms for some basic problems. In this module we are going to discuss about how to analyze the algorithms. First, the correctness of algorithm is very much need of the hour. First, the algorithm should really work. But once the algorithm works, then we have to start worrying about the efficiency of the given algorithm. So in this module we are going to discuss about how to analyze the simple iterative algorithms. The learning objectives of this module are these facts. Number one is we want to understand the process of algorithm analysis. We want to categorize the algorithm analysis into mathematical analysis and empirical analysis, and we are going to deal with how to analyze the iterative algorithm using the concepts of step count and operation count, and using this we can come to a conclusion about the efficiency of the algorithms. All these concepts are coming under the domain called algorithmic complexity theory. Algorithmic complexity theory is the sub-branch of algorithm study where we are going to deal with the efficiency aspects of algorithms. What is an efficient algorithm? An efficient algorithm is one that uses lesser amount of computer resources. By computer resources we mean memory, time, disk width, bandwidth, etc., etc. So any efficient algorithm should use the minimum of these resources. So the need of the hour is to analyze a given algorithm to know whether it is really efficient or not. But algorithm analysis is not an easy task. It is complicated because of various reasons. We have many factors like speed of the machine, that means the brand of the machine, programming language, the efficiency of the compiler in translating these programs, then program size, data structures used, and also there are many factors like algorithm style, ease of implementation, understandability of the algorithm, and also the simplicity of the algorithms. All these factors come into picture when we want to make a analysis of an algorithms. Fine. Before that we have to address one question. Why we have to analyze? The analysis becomes important of two reasons. Number one is we want to measure the efficiency of the given algorithm, because as I said earlier, the computer resources are very meager. So we want to design an algorithm that utilizes these resources in an optimized way. Second reason why algorithm analysis are important, because we want to compare algorithms. As I said earlier in the last module, for a given problem there may be many solutions. For example, if I give you a problem to a class, many students will design algorithm in a different manner. We want to compare which algorithm is better. So that is the reason why algorithm analysis becomes very important. Fine. Now we will address this particular question. If I want to compare algorithm, on what basis I should compare? These things are called measures or metrics. Using the metrics only we are making comparisons. For discussion's sake, we can categorize measures into two categories: subjective measures and objective measures. In subjective measures, we are going to deal with factors like ease of implementation, the algorithmic beauty or aesthetics, and understandability of the algorithms as a measure for comparing algorithms. For example, for a given problem, if two algorithms A and B are available, then I can use these measures to compare and to say which algorithm is better. But there are certain disadvantages associated with subjective measures, because these measures vary from person to person and even from time to time. For example, what appears to be a very attractive algorithm today may not be very attractive algorithm even for me. So, how to avoid these sort of problems? So, here only we encounter the concept of objective measures. Objective measures are mathematical ways of making comparisons. These are metrics that are based on solid mathematical foundations and principles. The necessary characteristics of an objective measures are listed below. Number one is measurability. That means we should be able to measure in terms of a formula. Then quantifiable, I should be able to quantify that into some sort of a compact number, and the formula computation should be very easy. Not only that, I should be able to make a prediction based on the computed number. These are called the characteristics of objective measures. In algorithm analysis, we will be discussing lots of resources like this. Some of the measures that we can use are running time, memory space, disk usage, and network usage. Out of all the things, time and space are very popular measures. So, time tells about the measurement of time, and space complexity deals with how much space that is utilized by the given algorithms. First, we will concentrate on time complexity. What is time complexity? Time efficiency or time complexity means how much runtime an algorithm takes for executions. This is what we are calling as time. When we say time, there are two times we are dealing with. Number one is runtime and another is compile time. Compile time is not very important for algorithm analysis because it is independent of the given instance, and also a program may be compiled again and again many times. By calculating all the times, we are not going to gain much of the insight about that particular algorithm. Therefore, in algorithm analysis, we always bother only about runtime. Runtime is also called as the execution time, which measures how much time an algorithm takes to compute the given instances. Time complexity is always measured in terms of CPU cycles. It is not in terms of seconds or hours, but always the unit of that is going to be in terms of CPU cycles. The general environment of algorithm analysis is going to be like this. We are going to take an algorithm of size n as input, and we are going to perform the algorithm analysis, and the output of this is going to be T of n. In other words, this is what we call as the time complexity in terms of the input instance n. Let us refresh some of the basic terminologies we have used. Number one is instance of an algorithm. Recollect from module 1 that any valid input from the legal set of domain is called an instance. For example, if I say I am going to write a program for sorting, any valid integers can be called as an instance of the given sorting problem. For algorithm analysis, size is very important. So, we have to define the input size. Input size is the length of the algorithm input. That means, for example, if I give an array of size n to a sorting program, then the input size can be called as n. Formally defined, input size is the logarithm of the input bits necessary to encode the input of the algorithms. In other words, we are using logarithm to represent the number of bits necessary to encode the input. Fine. What is the problem with this particular approach? The problem with this approach is we are trivializing the concept of analysis as a sort of input size. For example, you take the problem of primality testing. What is a primality testing? In primality testing algorithm, we are taking a number and then we are trying to check whether the given number is prime or not. Suppose if we take the number as 1, then the algorithm should be termed as an easy problem, but actually speaking, primality testing is a very difficult task. So that is the reason why we are taking the number of bits that is necessary to encode the number as a measure for representing the input size. Primality testing of a smaller number should not cause any problems, but on the other hand, primality testing of a very large number is going to be a problematic. That is why we said the input size is going to be the logarithm of the input bits necessary to encode the input of the algorithms. Why logarithm is necessary? Logarithm is necessary to make a bigger number as a smaller number. As you can see very well, if n is going to be 1024, then when we take logarithm to base 2, suddenly it comes down to a smaller number. So because of this purpose only, we are using logarithm. In other words, if the input is 5, then we are taking the binary equivalent, then based on that the size is calculated. Then once we calculate the size, then we are trying to express complexity in terms of the input size. That means we are trying to scale the input size, and based on that we are trying to predict the behavior of the algorithms. Why? For example, sorting of 10 numbers is a easy task, but sorting of 1 million number is a difficult task. So here the difference between these two instances is that algorithm is same, but the input size do actually matter. Therefore, we are trying to do analysis actually in terms of the input size and also using the concept of scaling. Fine. How to analyze? Let us come to the core aspect of this particular module. Fine. I am given a problem. I have written an algorithm. So now I want to analyze. So there are two ways of analyzing the algorithms. Number one is a priori. It is also called as the mathematical analysis, and another method is called the posteriori or the empirical analysis. So the first method is called the mathematical analysis, where we are trying to follow these sort of procedures. So the steps are listed here. Number one is we have to measure the input size, and we are trying to estimate the runtime either in terms of the step count or the count of basic operations, and based on that we are trying to make an estimation of the worst case, best case and average case efficiency of the algorithm, and finally we are going to estimate the rate of growth. Based on that the algorithm analysis is made. So in mathematical analysis, what we are trying to do is we are trying to do this sort of estimation before the code is written. So this is the major advantage of mathematical analysis. On the other hand, in posteriori, what we are trying to do is we are trying to write an algorithm, then we try to implement that as a program, and once the program is actually getting implemented, we are going to give a benchmark of data, and basically Based on that, we are trying to estimate time. Both has got its own plus point and minus point, but mathematical analysis is a preferred method because it is done before the actual algorithm is getting implemented. So now we will bother about how to analyze the given algorithms. So there are two ways of doing that. One is called step count and another is called the operation count. Both represents two schools of thought. One school of thought, that is based on the Ullmann study, is that step count is the basis of algorithm analysis. In other words, given an algorithm, we have to calculate how many steps are there in the algorithm, and the complexity of the algorithm is based on the step size. That is what the Ullmann school of thought goes. Another school of thought is, rather than based on step count, we can actually compute the operations. In other words, how many operations are there as part of the algorithm, and based on that we can say what the complexity is all about. All the textbooks are written based on both these schools. So let me introduce both these approaches as part of this particular module, so that you can have some sort of an idea about both schools of thought. Fine. What is a step count? In this school, the idea is very simple, where we have to count the instructions that are used by the given algorithms. So for that we have to precisely define what is a step. So a program step is nothing but syntactically or semantically a meaningful program segment. Any statement which I put as part of my algorithm which meaningfully does some task can be called as a step. So the logic of this particular school is represented like this. The logic goes something like this. So given an algorithm, we have to determine the total number of steps. So that means I have to find the number of instructions that are given as part of that particular algorithms. Once I find that, then I have to find the number of steps or the contribution by each statement. So that means it can be 1, or if it is a function, then it may be more than 1. I have to compute the steps and I have to compute frequency. Frequency is formally defined as how many times that particular step is carried out as part of the algorithm, and once I multiply these steps per execution and frequency, I will have the total, and based on the total then I can compute the time complexity. This is what the school of step count says. Fine. These are some of the guidelines of how the step count is calculated. Declarative statements with no initializations means the step count is going to be 0. On the other hand, if any initialization is made like I equal to 0 or k equal to 0, then the step count is going to be 1. And all the comments brackets like begin, end if, etc. will have a step count of 0, because the compiler is not going to execute all these things, and all the expression will have a step count of 1, and this assignment statement, function invocation, return statements will have a step count of 1. On the other hand, the functions sometimes may have more than one step. In that case, the steps per execution will vary. These are some of the guidelines using which the computation is calculated. Fine. I am taking one simplest example, and let me demonstrate how this step count is carried out. So, I am trying to interchange two numbers. So, this is the algorithm interchange a comma b. You can see very well I am carrying out certain task for interchanging the values of these two variables. You can see the first column steps. So, you can see very well this is 0, this is 0 because these statements are not executed by the compiler. So, you can see very well these three statements are executable statements. So, therefore, step is going to be 1 1 1 for this. This column tells the frequency, like how many times these steps are executed. Again you can see very well these are all ones. So, when I multiply these two, I am getting total. Now, you can see very well this is what the total is all about. So, when I add everything, fine, I am going to get 3. What does it mean? It means that the time complexity of this particular algorithm segment is a constant. On the other hand, we can say that this is independent of the input instance. So, that means this is a constant type algorithm. Therefore, this algorithm is going to be faster because it is not dependent on the input size at all. So, in other words, these sort of algorithm should be easy to implement and to execute. That is what we are calling as the algorithmic behavior. Then we will take one more example. So, this algorithm is all about computing the sum of an array. So, you can see the algorithm is given here, algorithm sum. So, a comma n. So, I am initializing sum equal to 0. So, I am starting a loop I equal to 1 to n. So, under that I am trying to compute the sum of this particular array, and finally, once the loop is over, then I am returning the sum. Let us try to analyze this particular algorithms. So, step by step per execution you can see in this column. You can see very well 0 are meant for the statements that are non-executable. So, for other statements you can see very well the step count is going to be 1. Int I is a declarative statement where initialization is not made, therefore, it is going to be 0. So, you can see very well for rest of the things it is going to be 1. This column tells the frequency. You can observe that sum equal to 0 is going to be executed only once, and you can see very well this loop is going to get executed n plus 1 times, because n plus 1 is required to come out of this particular loop. So, when you multiply these two, you can see very well this is what the total is. Fine, if you compute everything, you will find that it is going to be 2n plus 3. In other words, the time complexity of this particular algorithm segment is going to be 2n plus 3. So, this is what step count is all about. Another school of thought, as I said earlier, is based on the operations. Fine, you take the algorithm and compute how many operations are there, and the idea is to compute to find the basic or dominant operations. Fine, these are some of the operations that normally you encounter in algorithms. So, the procedure for this school of thought is going to be like this. Fine, I am going to count the basic operations and I am going to simplify that, and based on that I am going to define the complexity. Fine, these are some of the rules. Recollect, in the last module we talked about control structures. So, this is sequence. For example, if this program segment is given and statement 1 executes m operations, statement 2 execute n operations, find this whole segment now requires m plus 1 operations. This principle is what we are calling as addition principle. This is an example of this. For example, if I say this, then it incurs a cost of C1, it can be 1, or it can be anything. So, in general we represent this as C1. This statement represents cost C2. Therefore, this whole segment takes the cost of C1 and C2. This is how the cost is calculated for sequence. In the case of iteration, in the case of branching, the cost calculation is like this. So, if condition C, then statement P, otherwise Q. So, in this case the time complexity is going to be the maximum of either this or this. So, this is the simplest example you can say. So, you can see very well the condition is checked at the cost of C1, and based on that what you say, the statements either this or this is going to be executed. Therefore, you can see very well the total cost is going to be lesser than or equal to C1 plus the maximum of these two. Third is the repetition. So, in that case you can see very well T of n is approximately n times the statement of that particular loop. In other words, this is a small example. You can see very well for this, you can see cost is C3, it is getting executed n plus 1 times. So, under that you can see very well these are all getting executed n times. So, naturally when you compute everything, fine, you will add all the things. So, C1 multiplied by 1, C2 multiplied by 1, C3 multiplied by n plus 1, C4 multiplied by n, C5 multiplied by n. So, you have these sort of things. So, finally, when you simplify everything, you can see very well you get this expression. So, when you remove all the things by means of a constant, find your T of n is expressed as a function a into n plus b. This is what the operation count is all about. This is another example. Again, you can see very well for every operation we are assigning a cost. We are seeing how many times it is getting executed. Finally, we are going to multiply this cost with the times to get this sort of an expressions. So, finally, when we simplify that, you can see very well T of n is going to be in terms of this particular expressions. Fine. In summary, we can come to a conclusion like this. Algorithm analysis is important for two reasons. Number one is it is very important to determine the efficiency of the algorithm and also to make comparisons among algorithms. So, two types of analysis are mathematical or empirical. Mathematical analysis are the analysis that are done before the code is implemented, and posteriori or empirical analysis is the analysis that is done after the code is implemented. Runtime can be computed using both step count as well as in operation count. So, in step count we have seen that we have to calculate the program steps as part of the algorithm, and then we are trying to express the complexity in terms of the step count. And in operation counts we are calculating the operations and we are trying to find the dominant operation, and based on that we are trying to express the complexity. In the next module we will just discuss about how to utilize the values which we are getting as part of this exercise to express the complexity in a more accurate manner. That means we are going to discuss about the various scenarios, the worst case, best case as well as the average case, and then afterwards we are going to discuss about the rate of growth, and based on that we will make a statement about the behavior of the given algorithms. So, thank you very much for being as part of this module. Thank you very much.